Good morning, class, and welcome to this lesson on blackbody radiation and Planck's constant. Today, we will be able to explain what a blackbody is and how Planck's constant came about because of it. So, think of by comparison or by contrast, think of a mirror. Okay, a mirror is a reflective surface. Okay, and if a incoming wave, an electromagnetic wave hits it, it's going to reflect off of it. The mirror is not going to absorb it. The mirror it does not absorb. It only reflects. Okay, so this is pure reflection. Light hits it, light bounces off of it. Okay, so let's think of something else now. Let's think of a plant. Okay, so we have a plant. Okay, it's a very nice plant here. With the plant, light comes in. We'll take sunlight. Some of it gets absorbed. Some of it gets absorbed, and then some of it comes off as green light. So if we hit a plant with white light, it's going to absorb most of it, and then the rest is going to give off as green light. So there's some absorption here and some emission of light. So now take a black body. I'm going to draw it as a square. Okay, a black body is a perfect absorber. Energy goes in and it absorbs it perfectly. It's also a perfect emitter. So if it absorbs it, it can also emit the light. It can also emit the light, but not part of it like here. Not like white light went in and green light came out. If red light came in, red light's going to go out. If blue light came in, blue light's going to go out. If white light goes in, white light comes out. It is a perfect absorber and a perfect emitter. Okay? So that is the concept of a black body, okay? It absorbs completely, it emits completely, not partially, okay? It is a theoretical thing, but we can get close with some materials. So I'm going to erase this. What we found, what scientists found with their materials is that as we increase the temperature, if we were adding heat to this thing, so we have a flame down here, we're adding heat to this black body. That's an awesome flame, by the way. Hope you like that. What happened was it was absorbing energy and it was giving off energy. Okay, so it's absorbing and emitting. And based off this absorption emission thing, we have this graph. So this is the graph of what was being emitted off the black body. Okay, so this is the radiation intensity per unit wavelength. So what does that mean? That means that, for example, when the temperature was 4,000 Kelvin, down here, we were receiving very, very little waves at 1500 nanometers. We were receiving a lot at about 800, and we were receiving very little around 400, 300 again. Okay? If we increase the temperature, the graph shifted to lower wavelength, higher frequency wave intensity. If the temperature goes up, the graph shifted over to lower wavelength, higher frequency. So you can see here that we had a whole lot around right around 500, very little around here at 200, little here as well. But so the graph went from its peak being right here to its peak being right here. So it shifted over to the left. So, and that kind of makes sense. That kind of makes sense because as we added more higher temperature, higher temp equals more energy. Okay, higher temp equals more energy. We get that. That's thermodynamics. That's a pretty simple concept. Well, because we have more energy, we have lower wavelength we have lower wavelength, higher frequency, which we know that lower wavelength, higher frequency is higher energy. Just like um, gamma rays have more energy than radio waves, because gamma waves are lower wavelength and higher frequency. Okay, so um, this is what the graph looked like. That makes sense. Classical physics was able to explain that. But what they didn't get is their assumption was this graph should look something like this. Okay, I'm probably not going to hit this right, but it was about the same at lower temperatures, but they assumed the graph should just keep on going up and up and up. Okay, this is what classical physics predicted. Okay, the wave theory. If I keep on adding more and more temperature, I should just keep on getting higher and higher intensity per wavelength. Okay, so that didn't happen. As you can see from our graph, experimentally it dropped off again. Okay, so Max Planck was the first to realize. Let's go back to our picture here. We have our emitter. We have our awesome fire, which I'm going to draw so well again. Okay, we have our fire down here, and we are having radiation. It's coming off, and we are able to collect this somehow. It was some sort of collector, okay? Something that can detect this radiation, all right? So, if I have radiation coming off of here, and most of it is at a peak, that makes sense, and there's only some of it is very, very high energy. Only some of it is very, very high energy. He had this concept that energy must come in multiples. Or energy can only have discrete values. Okay, energy can only have discrete values. And so based off this graph, that makes sense. Because if it takes a whole lot of energy, if this side of the graph, if this wavelength right here, we'll call that 300. If 300 nanometers requires a lot of energy, okay? Because 300 nanometers is a very high frequency, okay? High frequency, high energy. If it requires a lot of energy, only a few of them are going to be produced. Only a few of them are going to be produced. This is kind of like, it's kind of like a bell curve in a class of students, okay? You're going to have some students that have the low end of the curve. There's going to be a peak in the middle of what the average students get, and there's going to be a few students getting very high grades, okay? This is kind of the same thing. Only very little radiation can have very, very low wavelength. Very little radiation can have high frequency, okay? Very little radiation can have high frequency because this radiation comes in packets, okay? So there's going to be an average somewhere in the middle, and there's going to be a drop off on either side. And so he had this idea, and he thought this equation came up where energy of this electromagnetic wave is equal to NHF, where N is just a 1, 2, 3, 4. Oh, excuse me, 0, 1, 2, 3, 4. Where these are all, so N is just a multiple of HF. Okay, N is just a multiple of HF. And so H is what we call Planck's constant. We know this already. E over F. And he found that this constant is equal to 6.626 times 10 to the negative 34th joules seconds. Okay, and so this is very fascinating. Every time, if we have a certain amount of energy and a certain wavelength, it'll always come out to be H. It'll always come out to be H. So basically, certain frequencies can only hold certain amounts of energies. So certain frequencies can only hold certain amounts of energies. So that means energy is what we call quantized. Okay, energy is quantized. And so based off this black body radiation based off this concept of this graph. Just because he was able to see this graph dropping off like this at the end here instead of keep on raising up, he came up with the idea that energy comes in packets. Okay, it was later confirmed by Einstein. We already went over this, but I'll go over it real quick. Einstein had the photoelectric effect, and he had the idea of photons. And so I mean, once these two things hit, you have Planck earlier than Einstein. Planck came out. Einstein came out next with his thing. Once these two things hit, we basically had the birth of quantum mechanics or quantum physics. The idea that energy comes in packets. Okay, and this all started with Max Planck looking at this graph and going, why does the graph look that way? And he came up with this. And we have Planck's constant, which is possibly going to be considered one of the universal constants in physics.